Close your eyes and imagine Earth, not as it is today with its bustling forests, flowing rivers, and continents crowded with life, but as it was more than 1 billion years ago. The world you would see might surprise you. Oceans still stretched from horizon to horizon, waves still crashed against rocky shores, and the skies still shifted between blue days and star-studded nights. Yet something was different. For almost 1 billion years, an unimaginably long stretch of time, the planet seemed to pause, to hold its breath. This was Earth's so-called boring billion. The phrase was first coined by scientists to describe a vast interval of Earth's history, roughly between 1.8 billion and 800 million years ago, during which little seemed to change on the surface, compared to the dramatic events that came before and after, such as the rise of oxygen, the explosion of complex life, or the icy grip of global, snowball Earth periods. This billion years appeared strangely uneventful. No great evolutionary leaps were visible, no massive shifts in climate, no planet-wide catastrophes that reshaped the world overnight. To many geologists and biologists, it seemed as though Earth had pressed the pause button. But appearances can be deceiving. Calling this time boring is in some ways misleading, for even in stability there is mystery. While it is true that the boring billion lacked the fireworks of other ages, it was far from empty. The oceans were alive with microbial mats and colonies of cyanobacteria, quietly shaping the chemistry of air and sea. Supercontinents slowly drifted and collided, their movements subtle but significant. And deep within cells, unseen by the naked eye, the foundations for complex life were being laid. To understand why scientists chose such a name, we must first appreciate the pace of geological and biological change. Earth's history is written in layers of stone, and each chapter unfolds across millions of years. When researchers examined rocks from this billion-year span, they noticed an unusual pattern. The chemical composition of oceans and atmosphere remained surprisingly constant. Levels of oxygen plateaued, never climbing high enough to fuel complex animals. Fossil evidence suggested microbial life dominated, with little sign of innovation or expansion into new forms. The stability of the planet's climate left few dramatic fingerprints behind. For a long time, this stability was frustrating to scientists, searching for the big turning points in Earth's history. They craved events that could be studied in detail, sharp transitions that told clear stories. Instead, the boring billion offered sameness layer upon layer of rocks, fossils of simple microbes, oceans that looked chemically similar across hundreds of millions of years. It was like staring at a photograph that never changed, no matter how long you looked. And yet, when viewed from another angle, the boring billion becomes less a story of monotony and more a story of preparation. Like the calm before a storm, this era may have been essential for what came next. The first stirrings of complex cells, the slow accumulation of oxygen, the quiet shaping of continents, all of these were seeds planted during this boring time. Without them, the explosion of diverse life in the later Precambrian, and ultimately the flourishing of animals in the Cambrian, may never have happened. It is also important to remember that boring is a human judgment. To a geologist, the lack of dramatic upheaval may seem uneventful. To a biologist searching for complex fossils, the absence of animals may appear disappointing. But to the microbes of the time, drifting in sunlit seas, this was an age of abundance. To the continents, this was an age of growth and quiet reshaping. To the planet itself, this was 1 billion years of steady breathing, holding conditions stable enough to allow subtle, hidden changes to take root. The scale of 1 billion years is difficult to grasp. Humanity's entire history, the rise and fall of empires, the building of cities, the span of cultures, fits into only a few thousand years. The age of dinosaurs lasted about 180 million years, but the boring billion stretched for nearly a third of Earth's total history. Imagine pressing pause on the most dramatic events in the planet's story and letting 1 billion years pass in steady rhythm. That is what this era represents, a pause not of silence, but of balance. As you relax and prepare for the chapters to come, think of Earth during this time. Picture vast oceans glimmering beneath a slightly dimmer sun. Picture continents clustered together in supercontinents, ringed by quiet shorelines. Picture skies with only faint traces of oxygen, not yet enough to breathe. Picture a world of microbial mats spreading across shallow seas, slowly photosynthesizing, slowly building the conditions for what was to come. The boring billion may not have the drama of asteroid impacts or the chaos of mass extinctions, but it holds its own fascination. It is the story of what happens when the planet takes its time, when life evolves at a whisper instead of a roar, when hidden changes prepare the way for future revolutions. In the chapters ahead, we will journey through this billion years in detail. We will see how continents formed and drifted, how oceans stabilized, how life clung to simplicity, and how slow processes quietly transformed the world. Far from boring, this billion years was a time of hidden drama, a deep breath in Earth's story before the great exhale of complex life. Before we can step into the long stability of the boring billion, we must first understand what came before it. Earth did not begin calm. Its earliest chapters were filled with fire, chaos, and transformation. By the time the boring billion arrived, the planet had already survived violent birth pangs, cosmic bombardments, and dramatic chemical revolutions. What seemed like stillness afterward was only possible because of the groundwork laid in the ages before. Imagine Earth about 4.5 billion years ago. The planet was new, still gathering itself from the dust and rocks orbiting the young sun. Collisions were constant, some small, some massive. One of the greatest impacts came when a Mars-sized body, often called Theia, struck Earth with incredible force. The collision melted much of the surface, tilted the planet's axis, and hurled debris into orbit. Debris that eventually coalesced into our moon. From that violence, Earth became a world with tides, stability, and a companion glowing in the night sky. In the aftermath of this collision, Earth was a molten world. Slowly it cooled, forming a crust. Volcanoes erupted across the surface, releasing gases that built the first atmosphere. Steam condensed and fell as rain, filling basins with the earliest oceans. These first waters may have been joined by ice and minerals delivered by comets and asteroids, each collision adding new ingredients to the recipe of the planet. Life's stage was being set, but it was not yet ready. The early atmosphere lacked oxygen. Instead, it was filled with carbon dioxide, nitrogen, methane, and other gases. Oceans boiled and cooled, mixing minerals into chemical soups. Lightning flashed, volcanoes roared, and sunlight streamed down onto a planet that was dangerous but full of potential. Somewhere within these early oceans, the first spark of life appeared. The details remain one of science's great mysteries, but evidence suggests that simple cells began forming more than 3.5 billion years ago. They were small, invisible to the naked eye, but they represented the beginning of something extraordinary. These early organisms fed on the chemistry of their surroundings. Some lived near hydrothermal vents on the ocean floor, where mineral-rich water gushed from beneath the crust. Others floated in shallow seas, experimenting with ways to capture energy. A great turning point came with the rise of photosynthesis. Certain microbes, particularly cyanobacteria, discovered how to harness the power of sunlight. Using water and carbon dioxide, they created sugars for food and released oxygen as a byproduct. At first, this oxygen did not linger. It reacted with iron dissolved in the oceans, forming rust like layers that settled to the seafloor. These banded iron formations, still visible in ancient rocks today, are evidence of those early reactions. But over time, the balance shifted. By about 2.4 billion years ago, oxygen began to accumulate in the atmosphere. This transformation, known as the Great Oxygenation Event, changed everything. For the first time, Earth had a breathable sky, though not yet breathable for creatures like us. Many early microbes found oxygen toxic, and mass die-offs followed. But for others, oxygen opened new possibilities. It allowed for more efficient energy use, laying the groundwork for complex life to come. The Great Oxygenation Event was dramatic, but it did not instantly create a world like today's. Oxygen levels rose, but they stabilized at relatively low amounts. For hundreds of millions of years, Earth hovered in a balance, more oxygen than before, but not enough to fuel large animals. The skies turned blue, the seas rusted red, and ecosystems of microbes adapted to the new chemistry. Life remained simple, mostly single-celled organisms, yet the planet had taken a huge step forward. Meanwhile, the continents themselves were shifting. Earth's crust was divided into plates, moving slowly across the mantle. Around 2 billion years ago, landmasses collided to form a giant supercontinent called Nuna, sometimes also known as Columbia. Its mountains rose, rivers flowed across its surface, and shallow seas lapped against its shores. When supercontinents form, they influence climate, ocean currents, and even the evolution of life. Nuna was one of the first of these massive landmasses, a rehearsal for later supercontinents like Rodinia, Gondwana, and Pangaea. By the time Nuna assembled, Earth had already seen both chaos and revolution. Oceans covered much of the planet, skies carried traces of oxygen, continents had gathered into vast superstructures, and life persisted in microbial form. The stage was set for something new, but instead of rushing forward, the planet seemed to pause. This pause is what scientists later called the Boring Billion, beginning around 1.8 billion years ago. After the drama of the Great Oxygenation and the assembly of Nuna, Earth entered a period of relative calm. Oxygen levels stopped rising significantly. Climate remained stable. Life showed little outward change. To many researchers, it looked like a billion-year plateau, a time when Earth caught its breath. But to truly appreciate the Boring Billion, we must remember how far the planet had already come. From molten beginnings to oceans, from lifeless rocks to microbial mats, from oxygen, poor skies to oxygenated seas, Earth had already transformed itself. The quiet that followed was not emptiness but balance. As you drift deeper into calm, picture this prelude to the Boring Billion. See a planet reshaped by fire and collisions. See oceans glistening under a young sun, skies turning blue for the first time, and a vast supercontinent stretching across the globe. Imagine microbial life spreading silently, releasing oxygen, altering chemistry, yet remaining simple. The planet was ready for its long pause. The next chapter of Earth's story would not be explosive, but enduring. The Boring Billion was about to begin. The curtain rises on a new act in Earth's story, the beginning of the Boring Billion. It was around 1.8 billion years ago when the planet entered this remarkable era of stability. To the untrained eye, nothing seemed especially exciting. Oxygen levels hovered at modest levels. Climate remained steady. Life, though present, showed little sign of rapid innovation. Compared to the fiery drama that came before and the explosive diversification that came after, this billion-year stretch looked uneventful. Hence the name, boring. But appearances can be deceiving. The Boring Billion was not empty. It was a long chapter of subtle processes, quiet transformations, and deep undercurrents that shaped the planet in ways we are only now beginning to appreciate. To understand it, we must first imagine what Earth actually looked like at its dawn. Picture the continents, not scattered islands, but large landmasses joined into a supercontinent called Nuna. Vast stretches of rocky land rose above the seas, connected in ways unfamiliar to us today. These continents were not covered with forests or grasslands. Plants had not yet colonized the land. Instead, bare rock stretched for miles, weathering slowly under rains and winds. Along the shorelines, microbial mats, thin carpets of simple organisms, spread across tidal flats, altering the chemistry of the water around them. The oceans dominated as they always have. They were deep, wide, and filled with life, though not the kind we might picture. There were no fish, no corals, no whales. Instead, life was microscopic. Cyanobacteria floated near the surface, capturing sunlight and releasing oxygen. Other microbes lived in the depths, feeding on minerals, sulfur, and methane. The seas were a patchwork of chemical environments, some rich in oxygen near the surface, others still anoxic, lacking oxygen. In the deeper layers, above these seas, the atmosphere had stabilized. Oxygen existed, but only at low levels, perhaps 1 to 10% of today's concentration. This was enough to support the chemistry of new ecosystems, but not enough to fuel large, active creatures. For now, the world remained microbial. What made this period so stable? Part of the answer lies in Earth's geology. The planet's tectonic plates continued to shift, but at a slower, steadier pace. Mountains eroded gradually, rivers carried sediments quietly into shallow seas, and volcanic activity was less dramatic than in earlier ages. Instead of violent upheavals, the planet seemed to move into a rhythm, like a heartbeat slowing after a long run. Climate, too, found balance. Before the Boring Billion, Earth had swung between extremes, hot, volcanic worlds and icy episodes. But during this long stretch, temperatures evened out. The sun was fainter than it is today, yet greenhouse gases like carbon dioxide and methane kept the planet warm enough for liquid water to persist. There were no massive global glaciations, no runaway heating events. Instead, the climate settled into a range that supported stability for nearly a billion years. To some, this stability seems dull, but for life it was essential. It created a predictable world, one where ecosystems could endure without catastrophic resets. Microbes thrived in mats colonies and shallow marine environments. Stromatolites, layered structures built by microbial communities, were common, dotting coastlines with strange, dome-like shapes. Though life did not diversify rapidly, it spread steadily, filling niches across the planet. Yet hidden within this apparent stillness, slow changes were unfolding. The chemistry of the oceans shifted gradually. Nutrients like phosphorus and nitrogen circulated differently, influencing where microbes could grow. Trace metals such as molybdenum and iron became important in the metabolism of certain organisms. Subtle variations in oxygen created gradients where different forms of microbial life could specialize. The stage was being set quietly for the future explosion of complex life. Another key development during the early boring billion was the continued evolution of eukaryotes. These are cells with internal compartments, including a nucleus to hold DNA. Eukaryotes are larger and more complex than the simpler prokaryotic cells that came before. Evidence suggests that they may have first appeared around 1.6 to 1.8 billion years ago, right at the dawn of this stable period. Though they did not immediately dominate, their arrival was revolutionary. Eukaryotes would eventually give rise to plants, animals, and fungi, including us. But during the boring billion, they remained part of the quiet background, slowly experimenting with new forms. The boring billion also gave us some of the earliest supercontinents. After Nuna, another great landmass, Rodinia, would eventually assemble around 1.3 billion years ago. These massive continents influenced ocean currents, weather patterns, and the cycling of nutrients. By creating vast shallow seas along their edges, they provided habitats where microbial life could thrive. Even in stability, the planet was not frozen in time, it was preparing. From a human perspective, the boring billion might seem like a lull, a billion years of sameness. But in the vast sweep of geologic time, stability can be just as important as chaos. It is during calm periods that foundations are laid. The slow weathering of rocks fed oceans with nutrients. The steady cycling of gases built a more breathable sky. The quiet persistence of microbes refined the chemistry of ecosystems. The appearance of eukaryotes planted seeds for future diversity. As you drift into calm, imagine this world. See the vast continent of Nuna stretching across the globe. Picture shallow seas lined with stromatolites, their microbial layers building slowly, year after year. Envision oxygen rising gently into the sky. Not enough for animals, but enough to change the color of the air and the chemistry of the oceans. Imagine a planet that seemed quiet, even uneventful, but that was quietly writing the prelude to complexity. The dawn of the boring billion was not about drama, but about endurance. It was about a planet that had survived its fiery youth and now settled into balance. It was about a biosphere that remained simple but resilient, patiently preparing for revolutions yet to come. The curtain of stillness had fallen, but behind it the stage was being set. The boring billion had begun. To understand the boring billion, we must look not only at life in oceans, but also at the arrangement of Earth's land. Continents are not fixed. They drift slowly across the planet's surface, carried by the restless motions of plate tectonics. During the early part of the boring billion, the land was gathered into one of Earth's first great supercontinents, Columbia, also called Nuna. Imagine Earth from above, 1.6 billion years ago. Instead of the familiar pattern of scattered continents and wide oceans, there was a single vast landmass stretching across much of the planet. Surrounding it, the oceans were deep and wide, wrapping around a world very different from the one we know today. This was Columbia, a supercontinent unlike any modern arrangement. Geologists reconstruct Columbia's outline by studying ancient rocks scattered across today's continents. Fragments of its once united mass are now found in North America, Siberia, India, South America, and parts of Africa and Australia. Like pieces of a broken puzzle, they tell the story of a time when nearly all land was joined together. Columbia's assembly began around 1.8 billion years ago and lasted until about 1.3 billion years ago, making it a central feature of the boring billion. What was life like on this massive continent? Unlike today's continents, Columbia was barren. No forests, no grasses, no animals roamed its surface. The land was mostly rock, broken by volcanic plains, mountains, and shallow basins. Rivers cut across its surface, carrying sediments into surrounding seas. Winds swept over bare ground, shaping deserts and dunes. Along its coasts, microbial mats formed in shallow waters, giving life a foothold at the boundary between land and ocean. The sheer size of Columbia influenced global systems. Supercontinents affect ocean circulation by reshaping currents. With so much land clustered together, the surrounding seas may have developed large, stable gyres, slow-moving whirlpools of water that circulated nutrients across the globe. These currents help distribute heat, stabilizing climate and reinforcing the relative calm of the boring billion. Columbia also influenced the atmosphere. As rain fell on bare rock, it slowly weathered minerals, releasing nutrients like phosphorus into rivers and seas. This weathering fed microbes, fueling the slow but steady production of oxygen through photosynthesis. At the same time, the erosion of mountains drew carbon dioxide out of the atmosphere, locking it into rocks. These processes kept Earth's climate relatively stable, preventing extreme swings between ice and fire. Geologically, Columbia was a time of stability, but not of stillness. The supercontinent itself was constantly shifting, pulled by the deep motions of the mantle. Cracks opened in its crust, creating rift valleys where magma bubbled up. Mountains rose where plates collided. Volcanic eruptions added layers of new rock, while erosion wore them down. Over millions of years, Columbia slowly drifted, stretched, and eventually began to break apart. But for hundreds of millions of years, it remained Earth's dominant feature. This vast landmass also left behind important geological records. Some of the oldest mountain ranges we know today, such as parts of the Canadian Shield and Cratons in Australia, formed during Columbia's assembly. These ancient rocks hold chemical fingerprints of the oceans and atmosphere at the time. Within them, scientists find isotopes that reveal oxygen levels, evidence of microbial activity, and clues about how Earth's surface was changing. Columbia's existence also had profound implications for life. By creating wide continental shelves, shallow areas along coasts, it offered habitats for microbial mats and stromatolites. These shallow seas, bathed in sunlight, became laboratories for photosynthesis and the slow buildup of oxygen. Without such platforms, microbes might have been confined to smaller, isolated regions. Instead, they spread widely, covering shorelines with colonies that transformed the chemistry of oceans and skies. Yet the supercontinent may also have limited diversity. With so much land joined together, there were fewer isolated ecosystems. This may have reduced opportunities for life to evolve new forms. In contrast, when continents are scattered, different environments create pressures for innovation. During Columbia's reign, the lack of fragmentation may have contributed to the impression of stasis, the sense that evolution was moving slowly, that life was trapped in repetition. Still, Columbia was anything but lifeless. Imagine walking its surface. You would find mountains eroded into rolling hills, deserts stretching across the horizon, and rivers flowing into shallow, green-tinged seas. The air would feel different. Less oxygen, more carbon dioxide. The silence would be profound, broken only by wind and the crash of waves. At the shoreline, microbial mats would carpet rocks, slick and colorful, like strange living paint. The land was empty of animals, but the world was not empty of life. Eventually, Columbia began to fragment. Around 1.3 billion years ago, tectonic forces pulled it apart, setting the stage for the next great supercontinent, Rodinia. But before that breakup, Columbia had endured for 500 million years, longer than any supercontinent that followed. Its stability mirrored the stability of the boring billion itself, not dramatic, not explosive, but enduring, foundational, and quietly transformative. As you rest, picture the world during Columbia's reign, a single continent vast and stony, ringed by silent seas, a sky of muted blue thinly oxygenated, coastlines alive with microbial mats while the land remained empty and stark. The world looked quiet, even boring, but it was quietly laying the groundwork for future revolutions. The supercontinent Columbia reminds us that stability is not emptiness. It is the quiet heartbeat of a planet preparing for change. Though the land was barren, its presence shaped ocean's atmosphere and life itself. The boring billion was not a pause, but a preparation, and Columbia, stretching across the planet, was its stage. The boring billion has puzzled scientists for decades. Why did Earth, so dynamic in its earlier history, suddenly settle into a long stretch of calm? Why did oxygen rise only modestly, life remain mostly microbial, and geology slow its pace? To answer, we must look at the planet's inner workings, its geology, its cycles, and the deep forces that drive change. Earth is a restless planet. Beneath our feet, molten rock churns slowly in the mantle, pushing tectonic plates across the surface. Volcanoes erupt, mountains rise, continents drift, and oceans open and close. In earlier ages, these processes were violent and fast. Massive volcanic eruptions spewed gases, asteroid impacts reshaped continents, and oxygen levels swung wildly. But during the boring billion, that restlessness eased. Earth entered a phase of relative equilibrium, where geological activity continued but at a slower, steadier pace. One of the main reasons for this calm was the configuration of continents. The supercontinent Columbia, later evolving toward Rodinia, covered much of the Earth's land. When continents are spread apart, plate boundaries are more numerous and active. Ocean ridges spread faster, volcanoes erupt more frequently, and climates swing more widely. But when land is gathered into a single supercontinent, tectonic activity slows. Fewer plate boundaries mean fewer chances for dramatic geological shifts. The world becomes, in a sense, quieter. Volcanism, too, played a role. During this time, there were no massive flood basalts, the enormous lava flows that can cover continents and release vast amounts of carbon dioxide. Instead, volcanic activity was steady but not extreme, feeding gases into the atmosphere without overwhelming balance. This kept climate and chemistry stable. There were eruptions, but they did not plunge the planet into crisis. Weathering also contributed to stability. As rain fell on Columbia's vast landmass, it wore down rocks and carried minerals into the seas. This process, called chemical weathering, removes carbon dioxide from the atmosphere and locks it into rocks. With such a large supercontinent, weathering became a powerful regulator, drawing down greenhouse gases and preventing runaway warming. At the same time, it supplied nutrients to shallow seas, feeding microbial mats and sustaining life. Another factor was the cycling of oxygen. After the Great Oxygenation event, oxygen levels had risen but then plateaued. Cyanobacteria continued to release oxygen, but volcanic gases and reactions with minerals consumed much of it. In this balance, oxygen never reached modern levels. Instead, it lingered at a fraction of today's concentration. For life, this meant a world with just enough oxygen to sustain microbes and early eukaryotes, but not enough for animals. The atmosphere was stable but limited, reinforcing the impression of stagnation. Deep in the mantle, recycling also slowed. Subduction, where one tectonic plate sinks beneath another, still occurred, but at a steadier pace. This meant that nutrients like phosphorus and trace metals were cycled more slowly between the crust and the oceans. Without sudden bursts of nutrient supply, ecosystems grew steadily but not explosively. Life was not stagnant, but its pace of innovation was gentle, stretched over millions of years. The climate during the boring billion reflected this equilibrium. Earth avoided both the extreme glaciations of earlier and later eras and the runaway greenhouse conditions of Venus. Carbon dioxide levels remained relatively stable, greenhouse warming balanced the faint sun, and oceans stayed liquid. For nearly a billion years, the climate rarely swung into chaos. This predictability gave the impression of monotony, but it also provided an essential backdrop for the evolution of complexity. From a human perspective, stability can seem dull. We often look for drama, for great changes that mark turning points. But from the perspective of life, stability can be just as powerful as upheaval. For microbes, steady oceans and a predictable sky provided the perfect conditions to refine their biochemistry. For eukaryotes, emerging quietly during this time, stability allowed experimentation. Without the constant reset of catastrophic events, cells could evolve new internal structures and strategies. The geology of stability also left a record in rocks. Sedimentary layers from the boring billion are unusually continuous, showing fewer disruptions than those from other eras. Geologists find long sequences of shale and sandstone laid down steadily over millions of years. These rocks preserve traces of microbial life, isotopes that record atmospheric composition, and chemical markers of ancient oceans. In their quiet persistence, they tell the story of a world in balance. And yet, beneath the surface, change was still brewing. Rodinia, the next supercontinent, was beginning to form. Subtle tectonic movements slowly rearranged landmasses, setting the stage for future breakups. Deep in the oceans, eukaryotic cells were experimenting with complexity. Oxygen, though stable, was inching upward, creating niches for new forms of metabolism. The calm was not permanent, it was preparation. As you imagine this world, picture long coastlines where rivers emptied into shallow seas. Picture bare, rocky land under muted skies, without plants or animals. Picture stromatolites rising like strange domes in tidal waters, fed by nutrients eroded from mountains. Picture volcanic peaks releasing slow, steady plumes of gas into the air. Everything moved at a slower pace. Tectonics, climate, life itself. But beneath the stillness, foundations were forming. The geology of the boring billion teaches us that history is not always written in explosions. Sometimes it is written in persistence, in cycles that repeat steadily, in processes that move almost imperceptibly but reshape the world all the same. Without this billion years of stability, the stage for complex life might never have been set. The boring billion was not a pause in Earth's story. It was a deep breath, a quiet interval in which balance reigned. And in that balance, the seeds of future revolutions took root. If you could dive into Earth's oceans during the boring billion, you might expect silence and emptiness. There were no fish darting through the water, no corals blooming into reefs, no whales singing across the seas, yet the oceans were not lifeless. They were filled with invisible worlds, bustling at scales too small for the human eye to see. This was the age of microbes, the true rulers of the boring billion. Microbes had already been Earth's dominant life forms for more than 1 billion years, and during this long era of stability, they continued to thrive. They came in many varieties: cyanobacteria, which captured sunlight and released oxygen; archaea, which specialized in unusual chemistries; and simple bacteria, which fed on sulfur, iron, and other minerals. Though small, their numbers were vast, forming the base of ecosystems across oceans, lakes, and shallow seas. One of the most striking features of microbial life was its diversity of strategies. Some microbes used photosynthesis, turning sunlight into energy. Others lived in the dark near hydrothermal vents, where superheated water rich in chemicals spewed from the seafloor. These microbes fed on sulfur and iron, forming unique ecosystems far from sunlight. Still others floated in oxygen-poor waters, relying on methane or nitrogen for survival. The slow pace of the boring billion did not mean stagnation for microbes. Instead, it gave them time. In the absence of sudden mass extinctions, microbial communities became deeply established. They spread into every available niche: coastal mats, deep sediments, shallow waters, and open seas. Their steady persistence shaped the chemistry of the oceans, influencing oxygen levels, nutrient availability, and the cycling of carbon. Cyanobacteria, in particular, played a critical role. These tiny architects of Earth's atmosphere had already triggered the great oxygenation event hundreds of millions of years earlier. Now, during the boring billion, they continued their quiet work. In tidal flats, they built stromatolites, layered structures of sediment and microbes stacked over time. Stromatolites dotted coastlines around the world, forming domes and mounds that stood as monuments to microbial industry. For hundreds of millions of years, they were among the most visible signs of life on Earth. The oceans of the boring billion were chemically complex. Near the surface, oxygen photosynthesis accumulated, but only in modest amounts. Deeper waters remained largely anoxic without oxygen, and often rich in iron and sulfur. This created layered ecosystems where different microbes thrived at different depths. At the surface, cyanobacteria captured sunlight. Below them, purple sulfur bacteria absorbed light filtered through the water, using sulfur instead of oxygen for their metabolism. Still deeper, in the darkness, archaea and bacteria consumed methane or iron. Each layer formed its own community, woven together into a global web of microbial life. Among these microbes, something extraordinary was beginning to stir. The rise of eukaryotes. Unlike prokaryotes, which are simple cells without internal compartments, eukaryotes had nuclei to store DNA, as well as organelles, tiny structures that performed specialized tasks. They were larger, more complex, and more versatile. The first eukaryotes likely appeared near the start of the boring billion, perhaps around 1.6 billion years ago. These early eukaryotes were still microbial, but they represented a leap forward. Some formed symbiotic partnerships, incorporating other cells into their structure. One of the most important of these partnerships was with mitochondria, the energy-producing organelles that allowed cells to generate more power. This innovation laid the foundation for the eventual rise of plants, animals, and fungi. But for now, eukaryotes remained part of the microbial background, slowly experimenting with new forms of life. Why didn't eukaryotes immediately diversify into complex organisms? The answer may lie in the environment. Oxygen levels, though higher than before, were still too low to support large, energy-demanding creatures. Nutrient supplies were steady but limited. The oceans were stable but stratified, with chemical layers that constrained where life could thrive. In this environment, microbes remained the best-suited form of life. Efficient, adaptable, and resilient, though small microbial life left a huge imprint on Earth. Their photosynthesis influenced the atmosphere. Their metabolism cycled elements like nitrogen, sulfur, and carbon. Their remains accumulated in sediments, forming vast deposits of organic material that would later become fossil fuels. Even today, much of the oil and gas we use originated from the slow work of microbes during ancient times like these. Imagine floating in the shallow seas of the boring billion. The water is greenish, tinted by cyanobacteria. Beneath you, stromatolite mounds rise from the seafloor, their surfaces coated with slimy microbial mats. Tiny bubbles of oxygen rise to the surface, released by photosynthesis. In the distance, the ocean darkens into deeper, anoxic waters, home to strange microbial chemistries. There are no fish to dart past, no seaweed swaying, no shells crunching underfoot, only the quiet persistence of microbes, shaping the world one molecule at a time. For hundreds of millions of years, this was Earth's biosphere, a microbial planet. Life had not yet built forests, reefs, or animal kingdoms, but it had established the foundations. The slow, patient work of microbes during the boring billion set the stage for everything to come. They created oxygen niches, experimented with eukaryotic complexity, and maintained balance in the oceans. Without them, the later explosion of complex life would not have been possible. The dominance of microbes during this time teaches us an important lesson: life does not always need to be dramatic to be powerful. Sometimes persistence itself is the greatest achievement. The microbial world of the boring billion may seem simple, even monotonous, but it was quietly laying the groundwork for the diversity that would one day fill Earth's skies, seas, and continents. As you drift into rest, picture this ancient ocean world. It may look still, but in its microscopic depths, it was alive with endless activity, weaving the threads of life's story in silence. Oxygen is one of the most important gases on Earth, yet it has not always been as abundant as it is today. For much of the planet's early history, there was little or none at all. The Great Oxygenation Event, about 2.4 billion years ago, marked a turning point when microbes began releasing oxygen into the atmosphere. But after that initial surge, oxygen levels did not continue to rise rapidly. Instead, they entered a long plateau that lasted through the boring billion. This balance, neither too high nor too low, defined the chemistry of the oceans, the atmosphere, and the pace of evolution. Scientists estimate that oxygen during the boring billion hovered between 1 and 10% of today's levels. That is enough to sustain microbes and simple eukaryotic cells, but far below the levels needed for animals with high energy demands. The air, if we could breathe it, would feel thin, like standing on a mountaintop. Fires would have struggled to ignite. Aerobic organisms, which rely on oxygen to power their cells, would have lived modest lives. Oxygen was present, but never abundant. Why did oxygen remain so limited? The answer lies in balance. On one side, cyanobacteria and other photosynthetic microbes continued producing oxygen, releasing it into the air and oceans. On the other, the planet itself consumed oxygen through geological and chemical processes. Volcanic eruptions released gases like hydrogen and methane that reacted with oxygen, removing it from the atmosphere. Iron and sulfur in rocks absorbed oxygen as well, locking it away in minerals. These sinks kept oxygen from building too quickly, creating a steady but restrained level. In the oceans, the story was even more complex. Shallow waters near the surface often contained oxygen from photosynthesis, but deeper layers remained anoxic, rich in iron and sulfur compounds. This created stratified seas, layered environments where oxygen and anoxia coexisted. Different microbes thrived in each layer. In the upper waters, cyanobacteria released oxygen. Below them, purple sulfur bacteria absorbed filtered sunlight, using sulfur instead of oxygen. Deeper still, microbes fed on methane and iron in oxygen-free darkness. Oxygen was part of the story, but it had not yet conquered the depths. This delicate balance of oxygen had profound consequences for life. Too little oxygen, and eukaryotes could not expand beyond small, simple forms. Too much oxygen, and other gases like methane, an important greenhouse gas, would have been stripped away, plunging Earth into ice ages. The boring billion may have represented a kind of oxygen sweet spot, where levels were just high enough to support innovation, but low enough to maintain stability. Evidence for this oxygen plateau comes from rocks. Ancient shales and iron formations preserve chemical fingerprints of past atmospheres and oceans. By studying isotopes of elements like sulfur, molybdenum, and chromium, scientists can reconstruct how oxygen cycled through the environment. These records reveal a world where oxygen existed in pockets and layers, but rarely dominated. It was a world of gradients, not abundance. Even within this stability, oxygen levels were not perfectly flat. There may have been small fluctuations, local rises and falls that played out over millions of years. Some regions of the ocean may have become temporarily oxygen-rich, while others stayed anoxic. These shifts created opportunities for eukaryotes to experiment. In oxygenated niches, larger, more complex cells could thrive. In oxygen-poor zones, anaerobic microbes continued to dominate. This patchwork of conditions made Earth a mosaic of habitats, each with its own balance. The presence of oxygen also influenced climate. Methane, produced by microbes, is a powerful greenhouse gas. When oxygen reacted with methane, it reduced its concentration, weakening its warming effect. This balance kept Earth's climate stable, not too hot, not too cold, throughout the boring billion. If oxygen had risen too high, methane levels would have dropped sharply, possibly triggering global glaciations. If oxygen had stayed too low, methane might have accumulated, heating the planet excessively. Instead, Earth maintained a middle path. For life, the oxygen plateau may have been frustratingly slow. Evolution did not accelerate into animals and plants because energy supplies remained limited. But at the same time, this long period of balance may have been exactly what was needed to prepare for complexity. Oxygen was available, though modestly. Eukaryotes had the chance to adapt, refine their metabolisms, and experiment with partnerships like the one that produced mitochondria. In a way, the boring billion was a rehearsal, a quiet training ground for the revolutions to come. Imagine standing on a rocky coastline during this time. The air feels different, thinner and less nourishing than today's. Fires barely catch when sparked. The ocean stretches out before you, greenish near the surface from cyanobacteria, darker below where anoxia reigns. Invisible microbes fill every layer, each adapted to the chemistry around them. Above, the sky is calm, its oxygen content steady but never abundant. It is a world of balance, stable, enduring, and quietly transformative. The story of oxygen in the boring billion is not one of absence but of moderation. It reminds us that change in Earth's history does not always come in leaps. Sometimes it comes in plateaus, long stretches where balance holds, where systems neither collapse nor surge. In this balance, life found space to persist, to experiment, and to prepare. As you drift into rest, imagine oxygen rising in tiny bubbles from shallow seas, spreading into the air, and then being absorbed again by rocks and oceans. Picture a planet breathing in rhythm, not with excitement but with calm steadiness. The boring billion was not an age of abundance, but an age of balance, and balance is sometimes the most powerful state of all. During the boring billion, Earth's surface was far from static. Continents shifted, collided, and drifted apart, just as they do today, though at a pace that is difficult to grasp on human timescales. Among the most significant events of this era was the assembly of a supercontinent known as Rodinia. Its name, derived from a Russian word meaning motherland, reflects its role as one of the earliest great land masses to bring Earth's continents together. Rodinia began to form roughly 1.3 billion years ago and reached its full shape around 900 million years ago. It was not the first supercontinent in Earth's history, but it was one of the most influential. Its vast bulk stretched across the equator, a colossal landmass surrounded by broad oceans. For hundreds of millions of years, Rodinia remained relatively stable, shaping the climate, the oceans, and the life of the boring billion. Imagine Earth from space during this time. Instead of familiar continents scattered across the globe, one immense supercontinent dominates the view. Its interior stretches for thousands of kilometers, dry and barren far from the sea. Around its edges, shallow seas lap against coastlines, filled with microbial mats and colonies of cyanobacteria. Beyond, vast oceans encircle the land, their surfaces calm, their depths stratified. The planet looks at once familiar and alien, blue with seas, greenish with microbial life, yet dominated by a single, sprawling landmass. The assembly of Rodinia was driven by plate tectonics. Continents carried on the slow motion of Earth's crustal plates, collided and fused. Mountains rose where they met, forming ranges that would rival today's Himalayas. Subduction zones swallowed ocean crust, recycling it into the mantle. These processes happened over tens of millions of years, so slow that if you could watch the Earth in real time, nothing would seem to move. Yet given enough time, the face of the planet changed completely. Rodinia's existence reshaped Earth's environment. One of its most significant effects was on climate. A giant continent covering much of the equator altered patterns of heat and circulation. Winds and currents shifted, redistributing moisture and energy around the planet. The vast land area reflected sunlight differently than oceans, changing how much heat the Earth absorbed. These changes may have kept global temperatures steady, reinforcing the stability of the boring billion. Rodinia also influenced the oceans. Large landmasses affect how water cycles through the atmosphere. Rain falls on continents, rivers carry minerals to the sea, and erosion enriches coastal waters with nutrients. With Rodinia's immense size, these processes intensified along its coasts. Shallow seas around the supercontinent likely became nutrient-rich, supporting microbial life. Stromatolites, layered microbial structures, may have flourished here, thriving in sunlit shallows where oxygen was slowly added to the air. In the interior of Rodinia, however, conditions were harsh. Far from the coasts, vast deserts stretched under dry skies. With little rain reaching these regions, they became barren landscapes, dotted with mountains and rocky plains. Few signs of life would have been visible here, aside from microbial crusts clinging to the ground. It was a land both monumental and empty, a reminder that early Earth was not yet the green and fertile world we know today. Rodinia's formation also shaped the biosphere in indirect ways. The erosion of mountains fed minerals like phosphorus and iron into the seas, nutrients that supported photosynthetic microbes. These, in turn, contributed oxygen to the atmosphere, maintaining the delicate balance of the boring billion. Though life remained mostly microscopic, the conditions created by Rodinia may have set the stage for future leaps in complexity. Evidence of Rodinia's existence comes from ancient rocks scattered across today's continents. Geologists piece together its story by comparing mountain belts, magnetic signatures, and fossilized sediments from different regions. Rocks in North America, Australia, Siberia, and China all carry clues that they were once joined in this vast landmass. By aligning these clues, scientists reconstruct Rodinia's shape much like solving a billion-year-old puzzle. Though Rodinia was stable for a long time, it was not eternal. Around 750 million years ago, it began to break apart. Rifts opened, seas flooded in, and continents drifted away once more. But during the boring billion, it stood as a symbol of geological calm, its bulk reinforcing the sense of stability that defined the era. Imagine walking along Rodinia's coastline. The air is thin with oxygen, the sky clear and vast. Before you, shallow seas ripple gently, their surfaces dotted with mats of microbes. The land rises behind you, barren and rocky, with mountains in the distance. There are no plants, no animals, no signs of forests or grasslands, only rock, sand, and microbial life. The silence is immense, and yet, beneath the calm, Earth's interior is alive, slowly reshaping the planet, carrying continents together into a single mass. Rodinia reminds us that Earth is never truly still. Even in the boring billion, when climate and life seemed stable, the crust itself was in motion, building mountains, shaping oceans, and assembling continents. The planet's story is always one of change, sometimes fast, sometimes slow, but always ongoing. As you relax into quiet, picture Earth as it was then, a world dominated by one great continent, its edges alive with microbes, its heart silent and dry. Around it, oceans stretch endlessly, their surfaces calm, their depths layered in gradients of oxygen and anoxia. This was the stage on which the boring billion unfolded, stable, enduring, and monumental. If the continents of the boring billion were dominated by Rodinia, then the rest of Earth was a world of oceans. These waters covered most of the planet's surface, stretching vast and unbroken, their waves stirred by winds, their depths layered in mystery. To understand the boring billion, we must look to these oceans, for they were the true stage upon which life and climate played out. From space, Earth at this time would still have looked blue. Oceans shimmered under the sunlight, clouds drifted across the skies, and ice caps gleamed faintly at the poles. Yet beneath the surface, the chemistry of the seas was very different from what we know today. They were less oxygenated, richer in certain metals, and layered into zones that shaped where life could and could not survive. The upper layers of the oceans, the sunlit shallows and surface waters, were the most familiar. Here light penetrated, driving photosynthesis in microbial communities. Cyanobacteria and algae floated freely or clung to stromatolites in coastal shallows. These organisms released oxygen into the water, slowly enriching the surface with this vital gas. Yet oxygen rarely penetrated deep below, and in many places it did not reach the seafloor at all. Beneath the oxygenated surface lay vast stretches of water poor in oxygen, or entirely anoxic. In some regions, these waters were not only oxygen-free but rich in dissolved iron or sulfur. Scientists call such conditions ferruginous, when iron dominates, or euxinic, when sulfur does. Both types were common in the mid-Proterozoic oceans. For life, this meant limits. Microbes that could tolerate or even thrive in these conditions flourished, but complex organisms could not yet emerge. Imagine diving into these seas. At the surface, the water seems much like today's oceans, clear and shimmering. Microbes float invisibly, their colonies forming faint greenish tints in the sunlit zones. But as you descend, the water grows darker, heavier, and different. Oxygen fades. Strange chemistries take over. In some regions, iron fills the water, giving it a murky, metallic quality. In others, sulfur compounds create toxic conditions. At the bottom, sediments accumulate, burying layers of organic matter and minerals that will one day tell geologists the story of these ancient seas. Despite their strangeness, the oceans of the boring billion were not lifeless. Microbial diversity was high, even if it was microscopic. Communities adapted to each layer. Photosynthesizers thrived near the surface. Anaerobic microbes made their homes in the dark depths, feeding on sulfur or methane. The oceans were alive with invisible activity, a quiet engine sustaining Earth's balance. One of the most important processes in these oceans was the burial of organic carbon. When microbes died, some of their remains sank into anoxic waters and were preserved in sediments instead of decomposing. This burial helped regulate carbon dioxide and oxygen levels, stabilizing climate over long timescales. Though changes were slow, this steady rhythm was part of what gave the boring billion its name. No great swings, just a calm balance maintained by the ocean's chemistry. The oceans also stored vast amounts of nutrients. Weathering of Rodinia's mountains washed phosphorus, nitrogen, and trace metals into the seas. These nutrients fueled microbial life, but not in the explosive way they would during later evolutionary radiations. Instead, the oceans remained a steady, subdued cradle of biology. Some scientists suggest that this nutrient-limited state held back the rise of complex organisms for hundreds of millions of years. Evidence for these ancient oceans comes from rocks that once lay beneath their waves. Shales, sandstones, and limestones preserve chemical fingerprints of the waters in which they formed. Iron formations reveal ferruginous conditions. Sulfur isotopes trace the presence of exynia. Organic molecules trapped in these rocks point to microbial life and its adaptations. Together, these clues reconstruct the hidden world beneath the waves. The oceans also interacted with the atmosphere in crucial ways. Carbon dioxide dissolved into surface waters, balancing levels in the air. Oxygen released by microbes sometimes escaped into the atmosphere, but often it was consumed by reactions in the sea. This tug of war between water and air kept the climate stable, preventing runaway warming or cooling. In many ways, the oceans were Earth's great stabilizers, absorbing change and smoothing extremes. Yet, for all their calmness, these seas were full of potential. Buried organic matter stored energy and carbon that, millions of years later, would influence the rise of oxygen and the emergence of animals. Microbes experimented with new metabolisms, finding niches in oxygen-poor and sulfur-rich zones. These quiet innovations would eventually pave the way for complexity. The oceans of the boring billion were not dramatic, but they were patient laboratories, preparing for revolutions to come. As you rest, picture the vast stillness of those seas. Waves ripple gently above, stirred by winds under a dimmer sun. The surface sparkles with light, but beneath lies a world of shadows, layered in chemistry, alive with microbes unseen to the eye. In those depths, balance is kept slow and steady across millions of years. Nothing seems to change, yet everything is in quiet motion, waiting. The oceans remind us that not all progress is dramatic. Sometimes, the most important work happens invisibly, silently, and steadily. The boring billion seas were like this, quiet, stable, enduring. And within that stillness, life endured, prepared, and evolved. In the next chapter, we will explore how oxygen, the invisible breath of life, behaved during the boring billion. For though it had begun to rise in the atmosphere, its levels remained low, fluctuating gently, never yet surging into the abundance we rely on today. When we think of Earth today, we take oxygen for granted. Every breath fills our lungs with the gas that fuels our cells. Oxygen makes up about 21% of the atmosphere, sustaining animals, fires, and countless chemical reactions. Yet during the boring billion, oxygen was scarce. It existed, but only in small amounts, never rising to the levels that would later support complex life. Understanding this period means exploring not just the oceans and continents, but also the thin veil of gases that wrapped around the planet. The story of oxygen begins long before the boring billion. Around 2.4 billion years ago, cyanobacteria in the oceans began releasing oxygen through photosynthesis. This event, known as the Great Oxygenation Event, transformed Earth's chemistry. Iron in the oceans rusted and fell to the seafloor, forming banded iron formations. The atmosphere gained its first significant trace of oxygen. Yet after this dramatic event, oxygen levels stalled. Instead of continuing to rise, they plateaued at relatively low levels, where they remained for over 1 billion years. This long pause is one of the defining features of the boring billion. Scientists estimate that oxygen in the atmosphere during this time may have hovered at less than 1% of today's levels, perhaps as little as 0.1 to 0.5%. That was enough to sustain some microbial life, but far too low for animals or even large, complex algae. The air was breathable only to microbes adapted to such lean conditions. To us, it would have felt suffocating, like trying to breathe at impossible altitudes. Why did oxygen stay low for so long? The reasons lie in the balance between sources and sinks. Cyanobacteria produced oxygen in surface waters, releasing it into the air. But at the same time, chemical reactions consumed it. Volcanic gases, rich in hydrogen and methane, reacted with oxygen and removed it from the atmosphere. Organic matter sinking into anoxic oceans also consumed oxygen as it decomposed. Even the crust itself absorbed oxygen, binding it into minerals. The result was a stable but low oxygen world. Imagine standing on the shores of Rodinia during this time. The sky is blue, the oceans ripple gently, the sun warms the land, but the air is different, invisible to the eye. It lacks the abundance of oxygen we rely on. Fires would struggle to burn. Animals, if they had existed, would have gasped for air. Only microbes, invisible to us, thrived in this thin atmosphere. The oceans played a crucial role in regulating oxygen. In the surface layers, oxygen accumulated as microbes released it. But in deeper waters, oxygen disappeared, consumed by reactions with iron, sulfur, and organic matter. This stratification meant that oxygen often could not escape to the atmosphere in large amounts. Instead, it was trapped, recycled, or consumed in the depths. For hundreds of millions of years, this ocean-atmosphere partnership maintained the status quo, just enough oxygen for microbial ecosystems, but no more. This period of low oxygen is sometimes called the mid-Proterozoic oxygen plateau. It is one of the most puzzling puzzles in Earth's history. For billions of years, life remained microbial. Complex cells appeared but did not flourish, and the atmosphere remained thin of oxygen. Only much later, around 800 to 600 million years ago, would oxygen begin to rise significantly, paving the way for animals. Evidence for this low oxygen world comes from the chemistry of ancient rocks. Sulfur isotopes, iron formations, and organic molecules all reveal the balance of oxygen in the oceans and air. Redox-sensitive elements, such as molybdenum and uranium, leave signatures that tell scientists how oxygenated waters were. These records confirm that the mid-Proterozoic world was one of scarcity, with oxygen never fully taking hold. And yet, this boring atmosphere may have been essential. By holding oxygen low for so long, Earth gave microbes time to evolve and adapt. It gave complex cells, the ancestors of plants and animals, a chance to develop slowly in protected niches. It prevented wild swings of chemistry that might have destabilized the planet. The pause of the boring billion may have been a kind of preparation, a long interval of balance that set the stage for what came later. As you picture this world, imagine skies clear and bright but thinner in spirit. Imagine oceans shimmering but poor in oxygen. Imagine microbial mats spreading across coastlines, quietly producing oxygen that never fully accumulated. It was a world of restraint, where the breath of life was present but subdued, a whisper rather than a shout. The stillness of this atmosphere may explain why the boring billion feels uneventful to us today. No great leaps in oxygen, no sudden rise of animals, no dramatic climate swings. Instead, the air remained stable, the oceans balanced, the planet calm. For over a billion years, this quiet equilibrium held, like a long pause in a symphony before the music swells again. As you settle into calm, reflect on how fragile balance can be. Oxygen was present, yet always held back, always consumed as quickly as it was made. The world was waiting for changes in geology and nutrients and biology that would one day tip the scales. But for the long stretch of the boring billion, the air remained light, calm, and thin. In the next chapter, we will see how life itself slowly adapted to this oxygen-poor world. Complex cells called eukaryotes appeared, experimenting with new forms and new strategies, even as oxygen levels remained low. They were small, quiet, and often invisible, but they carried the seeds of future revolutions. Life during the boring billion was not entirely stagnant. While microbes continued to dominate, something remarkable stirred beneath the surface of the seas. A new kind of cell appeared, larger, more complex, and capable of greater possibilities. These were the eukaryotes, and though their rise was slow, they represented a turning point in the history of life. To understand why eukaryotes mattered, we must first recall what came before. For billions of years, Earth was home only to prokaryotes, simple cells such as bacteria and archaea. They lacked a nucleus, their DNA floating freely in the cytoplasm. They thrived in every niche imaginable, from hot springs to deep oceans, but their simplicity limited their potential. Then, sometime during the Proterozoic, a new architecture emerged. Eukaryotic cells enclosed their DNA within a nucleus, built elaborate internal structures, and developed a capacity for specialization that would one day allow multicellular life. Imagine a microscopic world within those ancient seas. Most cells are tiny and plain, drifting passively or clustering into mats. But a few are different. They are larger with internal compartments. They move more actively, engulfing food instead of merely absorbing it. They have mitochondria, little powerhouses that allow them to use oxygen more efficiently. These cells are eukaryotes, and they are experimenting with new possibilities. The origin of eukaryotes remains one of the great mysteries of biology. The most widely accepted explanation involves endosymbiosis, a remarkable partnership between cells. According to this theory, a large prokaryotic cell once engulfed a smaller one, but instead of digesting it, the two formed an alliance. The smaller cell, perhaps an ancestor of modern mitochondria, provided energy. The larger cell offered protection and nutrients. Over time, the two became inseparable, merging into a single organism with combined abilities. This union may have happened more than once, giving rise to organelles like chloroplasts and photosynthetic eukaryotes. Eukaryotes were revolutionary because they could grow larger, store more DNA, and develop complex metabolisms. They could adapt to oxygen in ways prokaryotes could not. Their size allowed for greater diversity of form, and their internal organization paved the way for cooperation between cells. Although they remained microscopic during the boring billion, they carried within them the seeds of plants, fungi, and animals yet to come. But progress was slow. Oxygen levels were still low, limiting the environments where eukaryotes could thrive. Nutrients were available, but not abundant enough to fuel explosive growth. For hundreds of millions of years, eukaryotes coexisted with bacteria and archaea, often in small numbers. Fossil evidence is sparse but revealing. Microscopic fossils from this era include spherical or filamentous structures interpreted as early eukaryotes, some as old as 1.6 billion years. These tiny traces hint at a world where complexity was emerging quietly, almost invisibly. One of the challenges for eukaryotes was competition. Prokaryotes were extraordinarily successful, adapted to every niche, and often faster at reproducing. Eukaryotes, with their larger size and slower growth, had to carve out new strategies. Engulfing prey gave them an advantage in certain environments, allowing them to consume other microbes rather than relying only on dissolved nutrients. Photosynthetic eukaryotes developed later, adding new possibilities to the web of life. The significance of eukaryotes lies not only in their biology, but also in their persistence. Though small and few in number during the boring billion, they survived. They endured the low oxygen, the nutrient limitations, and the competition. And as conditions gradually shifted, they were ready to expand. Their resilience was a quiet rehearsal for the great evolutionary radiations that would follow. As you picture this microscopic drama, imagine looking through a drop of water from the boring billion seas. Most of what you see are simple bacteria, tiny and uniform. But here and there, a larger cell drifts, more complex, more active. Its nucleus shelters DNA, its mitochondria hum with energy. It engulfs another cell, digesting it within. It divides slowly but surely, passing on its complexity to the next generation. These are small beginnings, but they are the roots of everything we know. The story of eukaryotes during the boring billion is a reminder that progress need not be rapid to be profound. For over 1 billion years, they lingered in the background, small actors in a microbial world. Yet without them, the future rise of animals, plants, and humans would never have been possible. Their patience shaped the possibilities of life. As you drift into calm, reflect on the quiet persistence of these cells. Life did not leap forward suddenly, but prepared itself through small, steady innovations. In the stillness of the boring billion, eukaryotes endured, carrying within them the potential for forests, oceans filled with fish, and the rich diversity of life. In the next chapter, we will turn to one of the most iconic features of this age, the stromatolites. These layered microbial structures dominated shallow seas, leaving behind fossils that still stand today. They were the monuments of the boring billion, built not of stone alone but of life itself. When we picture ancient life during the boring billion, we must imagine a world without forests, flowers, or animals. The land was barren rock and sand, the skies thin in oxygen, and the seas filled mostly with microscopic organisms. Yet one form of life left visible monuments that we can still see today. These are the stromatolites, layered structures built by microbial communities, especially cyanobacteria. They were among the most successful life forms of the Proterozoic and symbols of the boring billion's quiet persistence. A stromatolite is more than a rock. It is a living partnership between microbes and minerals. Cyanobacteria in shallow seas trapped sediments and secreted sticky substances that bound particles together. Layer by layer, these mats built up domes, columns, or flat sheets of rock-like structures. Over time, the living surface continued to grow while the layers below fossilized. The result was a structure that could last for centuries, sometimes millennia, recording the daily work of countless microbes. Imagine walking along the shallow coasts of Rodinia. where the seas lap gently against rocky shores. Beneath the clear water, you see clusters of domed stromatolites rising like Nobi mounds. Sunlight streams down, feeding the cyanobacteria within. The microbes release tiny bubbles of oxygen, which drift upward and escape into the air. It is a tranquil scene, yet one that holds immense importance, for these structures were part of the slow oxygenation of the planet. Stromatolites were not new in the boring billion. They had existed since at least 3.5 billion years ago, some of the earliest fossils known on Earth. But during the Proterozoic, they were especially widespread, dominating shallow marine environments. With few competitors, they thrived, forming extensive reefs and mats across coastlines. For millions of years, they were the most visible evidence of life on Earth. The significance of stromatolites lies not just in their abundance but in their impact. By performing photosynthesis, cyanobacteria within stromatolites released oxygen into the oceans and atmosphere. Though oxygen levels remained low overall, stromatolites were part of the steady push that maintained balance and prepared the planet for future rises. Their growth also influenced sediments, shaping coastlines and stabilizing ecosystems in ways we still see echoes of today. Fossils of stromatolites provide a window into the microbial worlds of the past. Preserved in limestones and sandstones, they appear as layered domes or columns, often with intricate internal patterns. Each layer represents a moment in time, a season, a year, or even longer, like the growth rings of a tree. By studying these layers, scientists can learn about ancient environments, including water depth, chemistry, and even microbial diversity. Though stromatolites were dominant during the boring billion, their later decline tells another story. Around 1 billion years ago, the first signs of grazing organisms may have begun to appear: tiny, simple creatures that fed on microbial mats. Over time, as more complex life evolved, stromatolites lost their monopoly on shallow seas. Today, they survive only in a few places, such as Shark Bay in Western Australia, where conditions are too harsh for grazers to thrive. These modern stromatolites give us a glimpse of ancient seas, showing how microbial communities once shaped the planet. But during the boring billion, stromatolites were rulers of their domain. They were ecosystems unto themselves, providing shelter for other microbes, cycling nutrients, and altering their surroundings. They were not just passive structures but active participants in the global balance. Imagine peering closely at one, the surface alive with greenish mats, bubbles rising slowly, grains of sand trapped and cemented. It is a monument built not by stone but by life, growing grain by grain, cell by cell. The microbial worlds around stromatolites were equally important. Beyond cyanobacteria, countless other microbes filled the seas. Some fed on sulfur, others on methane or iron. They created invisible webs of interaction, each niche filled by organisms adapted to the conditions of their layer. These worlds were not flashy, but they were stable, resilient, and diverse. The quiet strength of microbial life sustained Earth through the boring billion. As you relax into calm, imagine drifting over shallow seas lined with stromatolites. The water is clear and still, the air quiet except for the faint sound of waves. Beneath you, microbial reefs stretch into the distance, domes rising and falling in gentle patterns. No fish dart, no seaweed sways, only the slow work of microbes, layer upon layer, building monuments of patience. Stromatolites remind us that life need not be grand to be powerful. Through steady persistence, these microbial architects shaped Earth's atmosphere, chemistry, and landscapes. They endured for billions of years, silently maintaining the cycles that kept the planet habitable. Though they are rare today, their legacy surrounds us in every breath of oxygen, every layer of limestone, every balance of the seas. In the next chapter, we will explore how the chemistry of the oceans during the boring billion influenced evolution. Iron, sulfur, and other elements cycled through the waters, creating both opportunities and limits for life. These chemical worlds determined what kinds of organisms could survive, and why complexity remained slow to rise. To understand life during the boring billion, we must first understand the seas in which it lived. These were not oceans like ours, rich in oxygen, teeming with fish, and filled with coral reefs. Instead, they were strange chemical worlds, murky, mineral-laden waters whose balance shaped the pace of evolution. For nearly a billion years, The chemistry of Earth's oceans acted as both cradle and constraint, allowing microbes to thrive while holding back the rise of more complex life. The oceans of the Proterozoic were layered. At the surface, shallow waters received sunlight and contained some oxygen, thanks to cyanobacteria performing photosynthesis. Below this thin layer, however, much of the ocean remained oxygen-poor or even completely anoxic. In many regions, the deeper waters were not only lacking in oxygen, but rich in dissolved iron or sulfur compounds. This made them hostile to most modern organisms, but ideal for specialized microbes. Scientists call these conditions a stratified ocean. Imagine floating above a Proterozoic sea. The surface looks calm, with cyanobacterial mats and stromatolites dotting the shallows. But if you dove below, the world would quickly change. The water would darken, its chemistry shifting. Oxygen would vanish, replaced by dissolved iron or hydrogen sulfide. Few organisms could survive here, but certain microbes thrived, harvesting energy from sulfur, iron, or methane. These invisible layers created a chemical puzzle. Life persisted, but complexity was restrained. One key feature of these oceans was the abundance of iron. In the absence of much oxygen, iron remained dissolved in the water. When oxygen did appear, released by photosynthetic microbes, it reacted with the iron, forming rust, like minerals that sank to the ocean floor. Over millions of years, these reactions created massive deposits of banded iron formations, alternating layers of dark iron-rich rock and lighter silica. These ancient rocks, found today in places like Western Australia and Minnesota, are direct evidence of the chemical tug of war between oxygen and iron in ancient seas. Sulfur played a similar role. In oxygen-poor waters, microbes used sulfate or hydrogen sulfide for their metabolism. This created zones where sulfur cycling dominated, producing chemical conditions very different from today's oceans. The smell of rotten eggs, produced by hydrogen sulfide, might have been common in these waters. For animals, such conditions would be deadly, but for microbes, they were opportunities. Different groups evolved to exploit every chemical niche, creating diverse microbial ecosystems. Nutrients, too, were part of the equation. Today, oceans are fertilized by elements like phosphorus and nitrogen, which support food webs from plankton to whales. But during the boring billion, the availability of nutrients was limited. Oxygen scarcity meant nitrogen cycles worked differently, restricting how much could accumulate. Phosphorus, often locked in rocks, entered the seas slowly. This scarcity acted like a brake, preventing microbial blooms from supporting larger, more complex organisms. Life survived, but it did not yet surge forward. These chemical balances help explain why the boring billion was, in evolutionary terms, boring. It was not that nothing happened, but that the environment set limits. Oxygen was too low for complex life to spread widely. Nutrients were too scarce to fuel explosive growth. Instead, microbes adapted to specific niches, creating stability rather than revolution. The oceans were like a carefully balanced laboratory, productive enough to sustain life, but not yet fertile enough to spark major transitions. Studying these ancient seas requires detective work. Rocks preserve chemical signatures that act like fingerprints of past conditions. For example, the ratios of different sulfur isotopes reveal whether oxygen was present or absent. The presence of certain iron minerals shows whether waters were anoxic or oxygenated. By combining these clues, scientists have reconstructed maps of ancient oceans, showing vast regions of oxygen-poor water stretching across the globe. It is humbling to realize how different the oceans once were. Today we think of the sea as a place of abundance. Schools of fish, coral reefs bursting with color, whales migrating across thousands of miles. But for much of Earth's history, the oceans were dominated by invisible life. Instead of colorful reefs, there were microbial mats. Instead of complex food webs, there were simple chemical cycles. The beauty of these seas was not in their variety of animals, but in the quiet persistence of microbes, endlessly adapting to their chemical world. And yet, within this chemical restraint lay the seeds of future change. Each pulse of oxygen released by cyanobacteria left a mark, oxidizing iron and altering the balance. Each cycle of sulfur or nitrogen added new complexity. Over millions of years, these processes slowly shifted the chemistry of the seas, preparing them for later revolutions. The boring billion was not a failure, it was a foundation. As you settle into calm, Imagine drifting through these ancient oceans. At the surface, cyanobacteria release tiny bubbles of oxygen catching the sunlight. Below, the water darkens into iron-rich layers, then into sulfurous depths where only microbes survive. The ocean is quiet, still patient. Every chemical reaction is a note in a slow symphony, building toward a future none of those microbes could imagine. The chemistry of the boring billions oceans teaches us a simple truth: life is shaped as much by its environment as by its own potential. For a billion years, Earth's seas were laboratories of balance, sustaining life but holding back complexity. When the balance finally shifted, the stage was ready for an explosion of innovation. In the next chapter, we will explore why oxygen remained so low during this billion-year stretch, and what small, steady changes eventually pushed Earth toward the next great leap in evolution. When we think of Earth today, oxygen feels abundant. It fills the air we breathe, drives our metabolism, and supports forests, animals, and oceans bursting with life. Yet for much of Earth's history, oxygen was scarce, so scarce that only microbes could flourish. During the boring billion, oxygen levels in the atmosphere and oceans hovered at a fraction of modern concentrations. The question is simple but profound: why did oxygen remain so low for so long? The answer lies in the balance between sources and sinks. Oxygen was being produced during this era. Cyanobacteria were alive and well, releasing it through photosynthesis. But at the same time, powerful forces consumed that oxygen almost as quickly as it appeared. For a billion years, production and consumption reached a delicate stalemate. Life continued, but oxygen never built up enough to fuel complexity. One major sink was Earth's rocks themselves. Early in its history, the planet's crust and mantle contained large amounts of reduced minerals, substances ready to react with oxygen. When oxygen entered the environment, it immediately combined with iron, sulfur, and volcanic gases, stripping it from the atmosphere and locking it away as solid compounds. Imagine oxygen as a guest arriving at a party, only to be pulled aside constantly by demanding hosts. Iron, sulfur, methane, all eager to claim it. Very little was left over for the atmosphere or oceans. Volcanoes also played a role. During the boring billion, volcanic activity was steady, releasing carbon dioxide, hydrogen, and other gases. Many of these gases consumed oxygen when they reacted in the air or water. For every pulse of oxygen released by cyanobacteria, volcanic gases pushed back, keeping levels low. The Earth's restless geology was, in a sense, in constant competition with biology. Another sink came from the oceans themselves. In oxygen-poor waters, microbes thrived on chemical processes that consumed oxygen or prevented it from accumulating. Sulfate-reducing bacteria, for example, produced hydrogen sulfide, which reacted with oxygen whenever it appeared. Methanogens produced methane, which could also draw down oxygen when broken apart in the atmosphere. These microbial communities formed a self-sustaining loop, stabilizing conditions that kept oxygen scarce. Nutrients further complicated the picture. The production of oxygen depends on photosynthesis, which in turn depends on nutrients like phosphorus and nitrogen. But during the boring billion, these nutrients were in short supply. Phosphorus, often locked in rocks, entered the ocean slowly through weathering. Nitrogen cycles, limited by oxygen scarcity, constrained microbial productivity. With fewer nutrients, photosynthetic microbes could not bloom on the scale needed to overwhelm the sinks. The planet's nutrient cycles kept oxygen production modest, reinforcing the balance. Scientists sometimes describe this balance as a low oxygen steady state. Oxygen was present, but only in thin layers, shallow surface waters, and perhaps a trace in the atmosphere. This was enough for microbes to survive, but not enough for animals requiring more energy. It was a world in which life existed, but at low metabolic gears. Evolutionary potential was waiting, but environmental conditions kept it locked. Evidence for this comes from rocks. By analyzing isotopes of sulfur, carbon, and iron, geologists can estimate ancient oxygen levels. The results show oxygen lingering well below 1% of modern atmospheric concentrations. Some estimates place it at less than 0.1%. For comparison, if oxygen levels today dropped even a fraction of that, most animals would not survive. During the boring billion, such low levels were the norm, not the exception. Why didn't oxygen eventually win? After all, cyanobacteria were producing it continuously. The answer lies in feedback loops. As long as sinks matched sources, oxygen could not rise. Whenever cyanobacteria released more oxygen, it simply reacted with reduced minerals or volcanic gases. Whenever nutrients allowed brief bursts of productivity, feedback systems pulled levels back down. Earth's environment was locked into stability, frustratingly stable from the perspective of evolution. This stability may actually have been crucial. If oxygen had surged too quickly, ecosystems might have collapsed. Rapid oxygenation could have poisoned microbial communities adapted to low oxygen conditions. By holding oxygen low, the Earth gave life time to adapt, diversify, and prepare for later transitions. In this sense, the boring billion was not wasted time, but a necessary incubation, allowing the planet to stabilize its cycles before moving on. It is also possible that plate tectonics played a role. During this era, continental growth was steady, not explosive. New continents released nutrients slowly, and subduction recycled carbon steadily. Without dramatic shifts, the cycles of carbon, oxygen, and nutrients remained in balance. It was a time of geological moderation, reflected in the chemical moderation of the atmosphere. The eventual rise of oxygen, long after the boring billion, required disruptions to this balance. Changes in continental configurations, pulses of nutrient delivery, and shifts in volcanic activity all helped tip the scales. But during the boring billion, the seesaw of oxygen remained level. Production and consumption matched so closely that oxygen stayed trapped in a narrow range for nearly 1 billion years. As you drift into calm, imagine Earth during this time. Shallow seas shimmer with microbial mats, releasing oxygen into the air. But as those bubbles rise, they vanish into reactions with iron, sulfur, and volcanic gases. The atmosphere remains thin, the oceans layered with anoxic depths. Life goes on patient, persistent, unhurried. The lesson of low oxygen is one of balance. Life wanted to push forward, but geology and chemistry held it back. For 1 billion years, the planet existed in a kind of chemical stalemate. And in that stillness, life waited, ready for the moment when balance would shift and oxygen could finally flood the world. In the next chapter, we will explore what that stability meant for ecosystems themselves, how microbes thrived in low oxygen environments and built strange, resilient communities that defined the boring billion. To imagine Earth during the boring billion, we must look beneath the surface of its shallow seas. This was a time when oxygen was scarce, yet life was not absent. Microbes ruled the world, building ecosystems that were both alien to us and astonishingly resilient. In these low oxygen environments, biology thrived in ways very different from the forests, reefs, and animals we know today. The seas of the boring billion were stratified. Near the surface, thin layers of oxygen existed, produced by cyanobacteria carrying out photosynthesis. These organisms floated in the sunlight, releasing bubbles of oxygen into the water and air. But just a few meters below, oxygen vanished. The deeper layers of the oceans were anoxic, meaning devoid of oxygen. In some regions, they were not only anoxic but also oxinic, filled with hydrogen sulfide, a chemical poisonous to most modern life. These conditions created sharp chemical gradients, dividing ecosystems into layers like tiers of a strange biological cake. In the oxygenated surface waters, cyanobacteria were the dominant players. They formed vast microbial mats, sometimes covering shorelines and shallow seas. These mats trapped sediments and built structures known as stromatolites, layered mounds of rock that can still be found in some places today. To walk along a shoreline during the boring billion would have meant seeing carpets of slimy mats rather than shells or plants. These mats were the factories of oxygen, though much of it never escaped into the wider world. Below the surface layer, other microbes thrived in the absence of oxygen. Sulfate-reducing bacteria lived in dark, oxygen-free waters, feeding on sulfur compounds and releasing hydrogen sulfide as a byproduct. This gas gave the deeper waters their toxic character and created harsh barriers for organisms moving between layers. Methanogens, another type of microbe, produced methane, a greenhouse gas that may have influenced climate. Together, these microbial groups formed stable, self-sustaining systems that recycled nutrients in ways utterly different from today's oxygen-rich oceans. In this low-oxygen world, complexity was limited, but not absent. Evidence suggests that eukaryotes, cells with internal structures like nuclei, appeared during the boring billion. These early eukaryotes may have lived in the thin oxygenated layers near the surface, taking advantage of the small but vital pockets of breathable water. Their appearance marks one of the most important innovations in life's history, even if they remained rare and subtle during this era. The ecosystems of the boring billion were not dynamic in the way we think of modern ecosystems. They did not support fast-moving predators, forests of plants, or diverse food webs. Instead, they were microbial mosaics, dominated by chemical interactions rather than visible organisms. The slow pace of life matched the slow pace of geological change. For hundreds of millions of years, these microbial systems endured stable and persistent, with few signs of upheaval. Still, they were not static. Microbes adapted to different niches, exploiting gradients of light, oxygen, and nutrients. Some lived in shallow lagoons, forming mats that built stromatolites layer by layer. Others lived in deep waters, thriving on chemical energy from sulfur or iron. Hydrothermal vents on the seafloor provided additional habitats, where microbes drew energy from mineral-rich fluids rather than sunlight. Life was everywhere water could support it, even if its forms were humble. The fossil record of this time is sparse, but stromatolites provide a window into these ancient ecosystems. These layered structures, built over centuries by microbial communities, are found in rocks from the boring billion across the world. They tell us that cyanobacteria were widespread and successful, shaping sediments and influencing local environments. Though they lack the diversity of later ecosystems, stromatolites remind us that life was active, building and transforming landscapes in its own quiet way. One striking feature of these ecosystems is their resilience. In low oxygen, high sulfide waters, microbes not only survived but thrived. Many of the groups that dominated the boring billion still exist today. In places like salt flats, hot springs, and deep sea vents, they are living fossils, reminders of the ancient world. By studying them, scientists learn how life can adapt to extreme environments, knowledge that helps us imagine life on other planets and moons. It is tempting to call the boring billion lifeless, but that would be misleading. Life was abundant, it simply operated at a microbial scale. From a human perspective, such ecosystems seem uneventful. But from the perspective of biology, they were rich, intricate, and essential. They laid the groundwork for later complexity, sustaining life through a time when oxygen was scarce and conditions were harsh. As you rest, picture these ancient seas. At the surface, mats of cyanobacteria shimmer in the sunlight, releasing oxygen into thin layers of water. Just below, darkness falls, and strange bacteria thrive in sulfide-rich depths. The ocean is quiet, still, patient. Life persists not in dramatic forms, but in subtle, enduring communities. The world waits and life waits with it. The ecosystems of the boring billion remind us that even in stability, even in apparent monotony, life finds ways to endure. They are a testament to patience, resilience, and the quiet strength of microbes. Without them, later explosions of complexity might never have been possible. In the next chapter, we will look at the first signs that this long stability was beginning to change, the subtle innovations in cells, metabolism, and ecosystems that hinted at the end of the boring billion and the dawn of a more dynamic Earth. Though the boring billion is often described as a time of evolutionary stillness, this picture is not entirely accurate. While ecosystems remained dominated by microbes and oxygen levels stayed low, important biological innovations were quietly unfolding. These were not dramatic explosions of diversity but slow, steady experiments in cell structure, metabolism, and cooperation. They set the stage for the revolutions that would eventually follow. One of the most significant developments during this era was the rise of eukaryotes, cells more complex than bacteria or archaea. Unlike their simpler cousins, eukaryotic cells contain internal compartments, such as nuclei to store DNA and mitochondria to generate energy. This internal organization allowed them to process more energy and support more sophisticated functions. Evidence suggests that eukaryotes may have first appeared before or during the boring billion, but it was in this long interval that they slowly diversified. Fossils from this time include microfossils with features consistent with eukaryotes. Some are larger than typical bacterial cells, while others show branching or complex shapes. These traces suggest that eukaryotes were experimenting with new lifestyles, even if they remained rare compared to microbial mats. For much of the boring billion, they lived in the shadows, never dominant, but quietly expanding their capabilities. Perhaps the most important innovation tied to eukaryotes was the development of symbiosis. Mitochondria, the tiny powerhouses inside eukaryotic cells, are thought to have originated as independent bacteria. At some point, an ancestral cell engulfed them, and instead of being digested, they formed a partnership. The bacteria provided efficient energy production, while the host cell offered protection. This merger was a turning point in evolution, one that made complex life possible. Without it, animals, plants, and fungi could never have evolved. During the boring billion, this process was taking hold, giving eukaryotes an energy advantage that would matter greatly later on. Other forms of symbiosis may also have arisen. Some eukaryotes likely formed partnerships with photosynthetic microbes, gaining the ability to harness sunlight more effectively. These experiments may not have flourished immediately, but they show that even in a world of microbial dominance, life was probing new directions. The patience of the boring billion was not idle. It was filled with trial and error at the microscopic scale. Innovation was not limited to cell structure. Metabolic strategies were also diversifying. Microbes explored new ways to harvest energy from their environments, tapping into gradients of sulfur, iron, and other elements. In shallow waters, some microbes specialized in photosynthesis under dim or filtered light. In deeper waters, others evolved to thrive in toxic, sulfide-rich conditions. These strategies reflected adaptation to the stable, but constrained environments of the time. Multicellularity may also have had its first stirrings during the boring billion. Fossil evidence hints at organisms that were larger and more complex than single cells, though not yet the fully developed animals or plants of later eras. These early multicellular forms may have been simple colonies, cells sticking together for mutual benefit, or they may have begun to show differentiation, with different cells performing different roles. Such steps were small, but they represented a shift toward greater complexity. In a sense, these innovations were like seeds planted in soil that was not yet fertile. The conditions of the boring billion, low oxygen, limited nutrients, stable environments, kept them from spreading widely. But when conditions later changed, those seeds were ready to grow into the forests, reefs, and diverse ecosystems of the Proterozoic and beyond. The billion years of seeming monotony provided the time and stability needed for these quiet experiments to take root. The fossil record of these innovations is sparse but tantalizing. Microfossils from this time include a variety of shapes, spheres, filaments, and branching forms. Some are large enough that they are unlikely to have been bacteria. Others show internal complexity, such as walls or compartments. Chemical traces in rocks also hint at the presence of sterols, molecules produced by eukaryotic cells. Together, these lines of evidence suggest that eukaryotes were present and slowly diversifying, even if they did not dominate. What emerges is a picture of life preparing for the future. During the boring billion, microbes did not vanish or lose importance, they remained central. But in their midst, new cell types were forming. New strategies were emerging and new partnerships were being tested. Life was rehearsing for the next act, even if the curtain had not yet risen. As you rest, imagine Earth's shallow seas filled with microbial mats. Within them, unseen to the naked eye, tiny eukaryotic cells go about their work, some with mitochondria, some experimenting with new shapes or partnerships. Imagine colonies of cells sticking together, just beginning to explore what cooperation might bring. These worlds are invisible to us, yet they carried the potential for everything that followed. The boring billion may appear uneventful on the surface, but it was rich in subtle change. It was a time of preparation, of small but profound steps that shaped the path of evolution. Without these innovations, later explosions of life would not have been possible. In the next chapter, we will turn to the continents themselves. During the boring billion, the supercontinent Rodinia began to assemble, reshaping geography, climate, and the conditions in which life unfolded. The story of land and sea was as important as the story of microbes, and together they defined the world of this billion-year span. During the boring billion, Earth's continents were not scattered as they are today. Instead, they were slowly moving toward one another, assembling into a massive landmass known as Rodinia. This supercontinent, whose name means motherland, was one of the great tectonic creations of Earth's history. Though the details remain debated, evidence suggests Rodinia came together between 1.1 and 0.9 billion years ago, during the heart of the boring billion. Its formation reshaped the planet's surface, influenced the oceans, and left marks that can still be traced in rocks today. To understand Rodinia, we must first imagine the process of plate tectonics. Earth's outer shell is broken into large plates that drift slowly over the mantle. Over millions of years, continents move, collide, and separate. At certain intervals, these collisions form supercontinents, vast landmasses that unite much of the Earth's crust. Before Rodinia, there had been other supercontinents, like Columbia. After Rodinia, others would follow, such as Pangaea. The assembly and breakup of these land giants is one of the rhythms of Earth's deep history. Rodinia is thought to have included most of Earth's continental crust. Reconstructions suggest that the core of the supercontinent lay near the equator. Laurentia, the ancient heart of North America, was central, surrounded by parts of South America, Africa, Australia, Antarctica, and Asia. The exact arrangement is uncertain, since the continents have since drifted far apart, but geological evidence such as matching mountain belts, mineral deposits, and paleomagnetic data help scientists piece together the puzzle. The creation of Rodinia was a slow process, taking hundreds of millions of years. Continents collided along vast mountain belts, where rocks were squeezed, folded, and uplifted. These collisions left scars, ancient ranges whose eroded remnants can still be found today. They also influenced the cycling of carbon, nutrients, and water between the land, oceans, and atmosphere. In this way, the assembly of Rodinia was not only a geological event but also an environmental one. The existence of a single, massive landmass had important consequences for climate and ecosystems. Large continents alter atmospheric circulation, changing wind and rainfall patterns. They also influence ocean currents, redirecting the flow of heat across the globe. With so much land clustered together, Rodinia may have experienced extremes of climate. Interior regions far from the sea might have been arid, while coastal regions saw different patterns of rainfall. These shifts affected the shallow seas where microbial life thrived, changing the distribution of habitats. Rodinia's formation also altered the supply of nutrients to the oceans. As mountains rose, they weathered slowly, releasing phosphorus and other key elements into rivers and seas. Though nutrient levels remained relatively low during the boring billion, these weathering processes helped set the stage for later increases in productivity. In a sense, Rodinia was preparing the world for future biological revolutions, even if its immediate impact was subtle. Another consequence of Rodinia was the stabilization of continents. Once assembled, the supercontinent reduced the number of continental edges where tectonic activity was intense. Fewer active margins may have contributed to the long stability of the boring billion, with less dramatic geological upheaval compared to other eras. The world was unified, quiet, and geologically steady, a setting that matched the biological stillness of the time. But Rodinia was not eternal. Like all supercontinents, it was destined to break apart. By about 750 million years ago, rifting began to split it into smaller pieces. This breakup would eventually set the stage for dramatic changes, including the snowball Earth glaciations and the rise of more complex life. But during the boring billion, Rodinia stood as a symbol of stability, a vast continent holding much of Earth's land together. The story of Rodinia is pieced together from rocks that bear the marks of ancient collisions. Mountain belts such as the Grenville orogeny in North America record the immense pressures of continental assembly. These rocks, with their folded layers and metamorphic minerals, are the remnants of mountains as tall as the Himalayas, long since eroded but still whispering of their former glory. Across the world, similar belts mark the sutures where continents joined, creating a geological map of Rodinia's construction. For life, Rodinia was both a challenge and an opportunity. The vast interior regions may have been harsh, with deserts and limited water, but along its edges, shallow seas and lagoons provided stable environments for microbial mats and early eukaryotes. The stability of Rodinia's geography mirrored the stability of its ecosystems. Together, They created a world that seemed unchanging to the eye, yet was slowly preparing for transformation. As you drift into calm, picture Earth during the age of Rodinia. A massive continent stretches across the equator, ringed by oceans. Mountains rise along collision zones, while interior regions bake in dry heat. Along the shores, microbial mats cling to rocks, quietly photosynthesizing. Above, the skies hold little oxygen, and the winds sweep across an ancient, unified land. The world is stable, still waiting. Rodinia reminds us that even in stillness, Earth is in motion. The assembly of a supercontinent is a slow dance of tectonic plates, invisible to daily life but monumental in scope. During the Boring Billion, that dance created a landmass unlike anything we know today, shaping environments and setting the stage for what was to come. In the next chapter, we will explore how Rodinia's climate shaped the world of the Boring Billion, how vast land, shallow seas, and long stability influenced weather, oceans, and the conditions of life during this billion-year stretch. When we imagine Earth's climate today, we think of shifting seasons, ice caps at the poles, and cycles of glaciations and warm periods. But during the Boring Billion, climate was remarkably stable. For nearly a billion years, Earth avoided the extremes of global ice ages or runaway greenhouse events. Instead, it lingered in a middle ground, warm, steady, and relatively uneventful. This stability was one of the defining features of the era, shaping ecosystems' oxygen levels and the pace of evolution. Why was the climate so stable? Part of the answer lies in the assembly of Rodinia. With most of Earth's land gathered into a single supercontinent, the planet's surface conditions were different from those of later times. Large landmasses reflect and absorb heat differently than smaller, scattered continents. Vast interior regions of Rodinia may have been dry and desert-like, but the planet as a whole remained in thermal balance. Winds and currents redistributed heat, preventing extremes. Another reason was the relatively steady cycling of carbon dioxide. Carbon dioxide, a greenhouse gas, plays a central role in regulating climate. When volcanoes erupt, they release carbon dioxide into the atmosphere, warming the planet. When rocks weather, carbon dioxide is drawn out of the atmosphere, cooling the planet. During the Boring Billion, both of these processes were in balance. Volcanic activity was steady but not excessive, while continental weathering proceeded slowly. Together, they created a self-regulating system that kept climate mild. The absence of major ice ages is particularly striking. Before and after the Boring Billion, Earth experienced periods of global glaciation, times when ice sheets may have covered the planet from pole to pole, known as snowball Earth events. But during the Boring Billion, such extremes did not occur. Instead, Earth's poles remained largely ice-free, and tropical regions stayed warm. This lack of extremes reinforced the sense of geological and biological stability. The oceans, too, reflected this climate balance. Without extensive ice sheets, sea levels remained relatively high, covering large areas of continental margins with shallow seas. These shallow seas were prime habitats for microbial mats and early eukaryotes. Warm waters allowed photosynthesis to continue steadily. Though low nutrient levels limited its productivity, the oceans were stable, stratified, and consistent, conditions that mirrored the climate above. Yet stability did not mean uniformity. Local climates varied, shaped by geography and ocean currents. Some parts of Rodinia's interior may have been hot and arid, while coastal zones experienced more moisture. Monsoon-like systems could have developed along certain margins, driven by the size of the supercontinent and its position near the equator. These patterns created regional diversity, even within the broader global stability. The chemical composition of the atmosphere also played a role. Oxygen levels remained low, but carbon dioxide and methane helped maintain warmth. Methane, produced by microbial communities, may have been especially important early in the Boring Billion. Its greenhouse effect compensated for the dimmer sun of that era, preventing the planet from freezing. Later, as oxygen levels inched upward, methane was reduced, but carbon dioxide continued to provide stability. Evidence for this steady climate comes from ancient rocks. Sedimentary layers from the Boring Billion lack the glacial deposits found in other eras, supporting the idea of ice-free conditions. Carbon isotopes from these rocks show little variation, indicating stable carbon cycling. Together, These records paint a picture of a planet locked in equilibrium, no dramatic swings, no sudden upheavals. This stability had profound implications for life. On the one hand, it limited evolutionary pressures. With no ice ages or drastic warming events, ecosystems remained steady and microbes could thrive without disruption. On the other hand, it provided the calm environment in which slow innovations, like the rise of eukaryotes, could take hold. The boring billion may have lacked drama, but its quiet allowed biology to prepare for future leaps. As you rest, imagine Earth during this time. Vast oceans shimmer under a warm sun, their surfaces calm, their depths stratified. A single supercontinent stretches across the equator, its interior dry and hot, its coasts lined with shallow seas. The skies hold a steady mix of gases, neither surging with oxygen nor collapsing into suffocation. Winds blow gently, storms come and go, but the overall balance remains unchanged for hundreds of millions of years. This image of stability is both comforting and uncanny. In our world of shifting climates and fragile balances, it is hard to imagine such long stillness. Yet Earth sustained it, holding steady for nearly a billion years. The boring billion was a time of patience, of balance, of quiet preparation. In the next chapter, we will explore how this long stability finally gave way. We will look at the geological and environmental changes that began to break the equilibrium, leading to the end of the boring billion and the dawn of a more dynamic, oxygen-rich, and biologically diverse Earth. Every story has a turning point, and so does the long stretch of Earth's boring billion. After nearly a billion years of balance and stability, the forces of geology, chemistry, and biology began to shift. Slowly at first, and then more dramatically. Earth moved out of its great equilibrium and into a new age of transformation. The ending of the boring billion was not marked by a single event, but by a gradual unraveling. Small changes that accumulated into profound transitions. The first signs of change appeared in the atmosphere. For hundreds of millions of years, oxygen levels had remained stubbornly low, locked at less than 1% of modern levels. Photosynthetic microbes had been producing oxygen, but chemical sinks, such as iron and volcanic gases, absorbed most of it. Then around 800 to 700 million years ago, this balance began to tip. Geological evidence suggests that oxygen levels started to rise again, a second great oxygenation that would reshape Earth. What caused this rise? One key factor was the continued activity of eukaryotes, organisms with complex cells. Their emergence during the boring billion may not have revolutionized ecosystems immediately, but over time, their efficiency in energy use and nutrient cycling began to matter. As they spread through the oceans, eukaryotes contributed more oxygen to the atmosphere and altered food webs, setting the stage for larger biological shifts. Another trigger came from the land, as Rodinia began to break apart. Continental rifting exposed new rock to weathering. This process drew carbon dioxide out of the atmosphere, reducing greenhouse gases and cooling the climate. It also delivered more nutrients, such as phosphorus, into the oceans. With more nutrients available, photosynthetic organisms could grow faster, producing more oxygen. The breakup of a supercontinent had geological consequences, but it also had direct biological impacts. Cooling temperatures pushed Earth toward its first major glaciations in nearly a billion years. Around 720 million years ago, the planet entered a series of snowball Earth events, times when glaciers spread near to, or even across, the equator. These dramatic ice ages marked a sharp contrast to the long stability of the boring billion. The shift was stark from warm, steady climates to extreme cold, from calm oceans to seas covered in ice. Earth was no longer boring. It was dynamic, volatile, and challenging. These changes had profound consequences for life. The oxygenation of the atmosphere and the delivery of nutrients into the oceans created opportunities for more complex organisms to emerge. The once dominant microbial mats faced competition from planktonic communities. Larger, multicellular organisms began to appear, supported by higher oxygen levels. Fossils from shortly after the boring billion include the first hints of early animals, sponges, and other simple multicellular life forms. The oceans themselves transformed. With more oxygen, the deep waters began to lose some of their stagnant character. Though anoxic zones still existed, parts of the ocean became more dynamic, mixing nutrients and oxygen more effectively. This new circulation supported evolving ecosystems. The long stillness of the boring billion gave way to motion and renewal. Geological records show the fingerprints of this transition. Carbon isotope ratios, which had been stable for so long, began to fluctuate, reflecting more dynamic carbon cycling. Glacial deposits reappeared in sedimentary rocks, evidence of the great snowball Earth events. Mineral deposits shifted as oxygen became more available, altering the chemistry of oceans and sediments. Earth's rocks tell us clearly the boring billion was ending, and a new age was dawning. The end of the boring billion was not only the close of a quiet chapter, it was the prologue to one of the most exciting periods in Earth's history. In the millions of years that followed, animals would diversify. Ecosystems would become more complex, and the planet would witness the Cambrian explosion, a sudden burst of life that filled the seas with creatures of astonishing variety. Without the stability of the boring billion, life might not have had time to develop the complexity necessary for this leap. And without the ending of the boring billion, the leap might never have occurred. As you drift into rest, picture this ancient Earth at the moment of change. The supercontinent of Rodinia is beginning to fragment, its vast landmasses breaking apart into smaller continents. Oceans lap against shifting coastlines, carrying nutrients into the water. Skies begin to hold more oxygen, the air just a little fresher, a little more supportive of life. And above all, the climate begins to cool. Ice creeping down from the poles, heralding the arrival of global glaciations. The ending of the boring billion reminds us of a profound truth. Even the most stable periods in Earth's history are temporary. Balance is never eternal. Eventually, new forces emerge, tipping the scales, driving evolution forward. What was once calm becomes dynamic, and what was once boring becomes transformative. In the final chapter, we will reflect on the lessons of this long, quiet era. We will see how the boring billion was not wasted time, but essential preparation for the flourishing of life. From stability came potential, and from potential came the vibrant world we now inhabit. When we think about Earth's history, it is easy to focus on the dramatic moments: the fiery birth of the planet, the rise of oxygen, the great extinctions, and the explosion of animal life in the Cambrian seas. Yet in between these highlights lies the boring billion, a stretch of time often overlooked, dismissed as dull or uneventful. But as we've discovered, this era was not boring at all. It was a billion years of balance, preparation, and subtle change. Without it, the story of life on Earth might have been very different. The boring billion, lasting from about 1.8 to 0.8 billion years ago, was a time of stability. Oxygen levels remained low but steady. The climate was warm, avoiding the extremes of earlier ice ages and later snowball Earth events. Continents were large and relatively stable, gathered into supercontinents like Nuna and Rodinia. Evolution moved slowly, dominated by microbial life, with only the first hints of complex eukaryotic cells beginning to appear. On the surface, it seems quiet, but beneath that quietness was a foundation being laid. One of the key lessons of the boring billion is the value of stability. Life requires more than sudden bursts of change. It also requires long, steady periods to adapt, refine, and experiment. In the oceans of this era, microbes evolved new strategies, forming partnerships, developing photosynthesis, and experimenting with more complex cell structures. These quiet innovations would later make multicellular life possible. Without the long runway of stability, biology might not have had the time it needed to take these steps. Another lesson lies in Earth systems themselves. The planet's geology, atmosphere, and oceans were locked in a delicate equilibrium. Plate tectonics kept continents moving slowly, recycling nutrients and gases. Volcanic activity balanced out gassing with weathering, keeping the climate warm but not extreme. Oceans remained stratified, with oxygen near the surface but anoxic depths below. This balance endured for hundreds of millions of years, longer than any human can easily imagine. It shows us that Earth is capable of sustaining equilibrium on vast time scales, but also that such equilibrium is never permanent. The boring billion also reminds us of how fragile progress can be. Complex cells, eukaryotes, emerged during this time, but their growth was limited by low oxygen and nutrient scarcity. They waited, as it were, for the right conditions. when oxygen rose at the end of the boring billion and glaciers began to reshape the planet. Those eukaryotes seized the opportunity, blossoming into the ancestors of plants and animals. The lesson here is clear: sometimes progress is invisible until the environment changes, and then, suddenly, all the groundwork reveals its importance. From a human perspective, the boring billion offers a kind of cosmic humility. Our lives are short, and we are drawn to the spectacular, the dramatic, the immediate. But Earth's history tells us that patience is as important